Now let's examine the observation strategies. What information do we need to know? And how do we determine our approach for conducting the observation? Let's select the object. The most typical scenario is that usually we encounter an astronomical problem as our initial challenge to solve. That when studying it, our conclusion is we have to use Mezcal. That is to say, we are going to think about extended objects, and we are going to think about finding their morphocinematic structure. Other astro issues may require Mezcal for resolution. But what we are going to talk about is this. Remember that this instrument was designed by Professor Miro precisely to understand the kinematics in gaseous nebulae. So, the entire group that collaborated with Professor Mayborn and all of us who have emerged subsequently, basically we have utilized this instrument to transform nebulae into our primary targets and concentrate our research efforts on them. For example, here we have a very beautiful image of Sven Eklund of the KJPN8 object. The object KJPN8 was discovered in 1994. The publication was released in 1995 by Professor Alberto Lopez through your server when I was pursuing my master's degree. Subsequently, we enlisted the support of Professor Luis Felipe Rodriguez to assist us in the radio broadcast of this item. It was discovered in San Pedro, and later studies were conducted on it, precisely with Mezcal, to know the kinematic structure of this object. This is a very beautiful image that I obtained on the web. The credit goes to Sven Eklund, and there is the website where you can check it out. Let's recall that we utilized the Mezcal in the 2.1 meter telescope when employing the f7.5 secondary mirror. So this, for the CCD, for example, with a size of 24 microns, projects an image of 0.31 arc seconds onto the sensor, in each and every minuscule pixel. That signifies then that the complete field of 1024 takes approximately 5 minutes. Very well, I understand. So, that leads us to believe that the most suitable candidates are those whose overall dimensions are approximately 4 minutes in duration. If they're younger, we'd have more space and fewer objects. If they're larger, we'd need one slit to cover the object. And another aspect to consider is that the structures we desire to observe can be defined in just a matter of seconds. If we have a resolution of 1 or 2 arc seconds, then the structures should be separated by at least 4 or 5 seconds in order to distinguish them. This is the case, e.g., of the 7309 nebula I mentioned. And there's the article, the first one generated. Well, how are we going to set the position angle in the slit? Initially, the platinum had a goniometer with a goniometer direction that extended from the north to the westward direction, as indicated by the goniometer's orientation. When discussing position angles in the sky, we transition from north to eastward direction. So, when I desire to utilize the position angle of 60 degrees, that corresponds to the plate located in the 300-degree position. Later, we created a project to automate the platform, and in essence, if we utilize the automated plate, we would not have to be concerned about this portion. However, I express it as a complementary component of understanding the instrument. So there are the equations that we had to utilize whenever possible. It is also extremely important that we always remain within approximately 90 degrees north, so that we do not have to make more than a 90-degree turn to the plate. In other words, we need to search for angles that complement each other. For instance, to ensure that the plate is not located elsewhere. For instance, it states, I desire the position angle of 150. Thus, it is preferable to position the plate at a complementary angle, which would be 30 degrees. So, as long as we are around the north at about 90, it is better to avoid problems with the instrumental part. Here is what it stated, subtracting 150 and adding 180 results in 30 degrees. Well, one of the fascinating aspects that Mezcal additionally accomplishes, and that is likewise highly significant, is its capability to capture both the direct image and an overlaid slit image that precisely indicates exactly where we are going through our trajectory. That is present within specific sequences, and that is commonly known as image plus slit. That is image plus slit. It is advisable to take the image more slit before, because it removes the mirror and leaves the slit there. That is what we are seeing like this was. To confirm doubt, take another image slit later, if there is any indication of movement or failures in the guidance system. And so we wouldn't have any problem. This is the case, for example, of obol 72. And there we see, for example, one of the cracks that we took where the most crack image is. That is crucial because it will aid our subsequent analysis of the objects and their morphocinematic structure. The other one is the second. The filters. Where are we going to observe? Regularly, to obtain the kinematics, we extract it with low excitation lines, such as nitrogen, or with high excitation lines, such as oxygen 3. On several occasions we have done in H-alpha. Why? Because H-alpha is the most abundant line. It has a larger quantity of electrons in additional parts of hydrogen, so the lines tend to be broader, and it is much more challenging, for instance, to outline morphokinematic structures. It is much simpler to do it, either with the forbidden lines of nitrogen or with the forbidden lines of oxygen 3. The sulfur lines are also interesting when it comes to very violent collisions, in which for some reason we cannot be seeing the nitrogen lines with a good intensity. But they are basically the ones we use to do morphokinematics. However, for anything else, any other gas that someone wants to see, 5 centimeter filters can be obtained, which are 2 inches, and then observations can be made in other orders of other wavelengths. These, for example, are observations of NGC 4361, a work that we also published, where you can see that we have separated the alpha line from the adjacent line that is very close, which is helium-2, and then we have the oxygen-3 line. It's an excited nebula, that's why we see helium-6560 with alpha 6563. Exposure time. How much time are we going to give to our exhibitions of our objects? Several things must be taken into account. If the CCD is 16 bits, it will saturate at 65,000 counts. Therefore, we should not exceed that limit. Unless we want to see the weaker areas even more and we have a way to saturate without caring about that part. No calibration without flow in Mezcal. Separation is of interest. In wavelength, flow calibration may be desired for certain projects, so it must be considered. Taking into account the exceptionally high dispersion, it is improbable to anticipate encountering substantial emission in the majority of objects under observation. So it is really challenging to achieve saturation. Usually, if I attain a level 40 or 50 higher than the background noise, I am satisfied with that. One of the techniques I prefer to employ as an initial step is a 20-minute period of exposure, and almost with those times I have no problem. There are some nebulae, very few of course, that with that we can saturate some of their regions. So, we have to be careful with that and use less time. You can use 10 minutes, 5 minutes. Alternatively, in the case of a very weak source, we can also opt to extend the exposure time to a duration of 30 minutes. I do not recommend exposures longer than 30 minutes. Why? Because during the process of exposing, it is similar to what I am describing. When is the light arriving, right? The load is accumulating. Yes? And if the load doesn't stop, we can play the image, which is the image of my hand. We have the ability to perfectly reproduce the image of my hand with utmost accuracy. Isn't that right? If the magnet was saturated, we wouldn't be able to see it. That's a good observation. What happens during an exhibition? Not only do we have this, but imagine that I can take out just one little nail. It's challenging. Envision that I'm able to eliminate only one small nail. There are tiny particles. In the cosmos, there exist electric charges known as cosmic rays. These electric charges, which are famous, directly arrive and get deposited in our detector. They do not pass through the spectrometer. In fact, they do not pass through us either. Additionally, they are also part of the factors that contribute to the evolution of living beings. However, that is a separate topic. Therefore, when we are exposing with a CCD, cosmic rays will fill our image with dots. It can make it difficult for us to calibrate our data. Part of the process is to remove cosmic rays. Therefore, I do not recommend exposures that exceed a duration of more than 30 minutes. If more time is needed, then what I'd say is, give it more. Give a new exposure to a new exhibition. And then there are techniques available to eliminate the cosmic ones, but also to enhance the noise signal as a sort of combination or aggregate of these emissions. I forgot about that, my memory failed me. That must be considered when determining exposure times. For plate scale, which mode do we want to utilize? There is something referred to as beaming. Beaming occurs when I demonstrate a minimum of 2 by 1, meaning squares that measure 1 pixel in both width and height. A minimum of 2 would be squares of 2 pixels. That is, everything within 4 pixels, I'll convert into 1. That reduces the reading time of the ECDs, that reduces the size of the final image, etc. However, it also diminishes the resolution. The resolution in both axes would be the spatial resolution along the slit axis and the spectral direction of the instrument. For example, the mentioned detector, initially 0.31 px and 0.05 A, becomes 0.62 arcsec and 0.1 A in 262 binning. In binning 2x2, this changes 62 arcsec and 0.1 A, okay? So, that would indicate that the minimum Gaussian we could have in the 2x2 is 1.4 seconds, the average power launch, and the full width half maximum of the spectral lines would be approximately 10 kilometers per second, which is the average speed of the spectral lines during the launch process. In general, those are acceptable numbers because the image quality, what we refer to as the seeing, is between 1 and 2 seconds. So having our best spectrum at 1.4 seconds is not bad. Although we are pointing out noise, the image is smaller. So, we can start working on beaming 2x2, which is the most natural. Now that we use 0.17 detectors, working on beaming 2x2 is almost mandatory, because the signal that would arrive in 0.17 pixels is very low. So, there we have a discussion about working on beaming 2x2 or even on beaming 4x4. Image taken from NGC 3354 in article by Dr. Maru Contreras. 4 in article by Dr. Maru Contreras. Well, this is the UI. Over time, it undergoes changes. Some things have already been changed. Some details have been modified to include additional elements. But essentially, we have the ability to configure the lamp, the filters, the bandages, and even the angles of what would be the diffraction grating, among other adjustments that can be made. Exposure time. That yellow button, for instance, is the one for sequences, enabling us to have all the steps needed to take, like 5 paths, or a comparison arc, or something similar, which are already quite determined. So essentially, what remains is to establish the exposure time for what will be our spectra. It is also specified in which directory the images would be saved, and below you can see the parameters of the CCD. In this case, a 1000x1000 CCD is being used with a 4x4 binning and a gain of 1. So one can configure if they only want to use a part of the CCD, and then on top of that, if they are going to use that part with a binning, etc. So, for example, now it has been included to take the position angle information. We can also include it, and we can also include some comments if we want all that to go as metadata information within the image headers. So, well, that's the interface.